Hi, we're Wiser Systems. I'm Seth Holler, CEO,
And I am Logan Maxwell, wearer of many hats.
and today's discussion is a little bit technical. We'll be talking about dun, 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 signal propagation, specifically,
Wow.
yeah, I know, specifically RF signals. Um,
Yes.
and Logan runs into this explanation, or he explains RF signal propagation a lot when he's dealing with clients or future opportunities. And so, what? How do we get started here?
Yes. Yeah. I think it's important to kind of set the stage and use representative examples that people might be able to understand because it gets really technical really fast.
Yeah, and a lot of time you find yourself explaining it because people have tried other technologies, right?
Yeah, yeah. I think a lot of times hey, we want to put Wiser in our plant. It makes a lot of sense. And they go, well, 2 years ago, we tried to put Bluetooth everywhere and it failed. Or we tried to do Wi-Fi tracking, or
Right.
we tried to do some active RFID. What makes this different? Why is this going to be any better?
Yeah.
Essentially. So,
And so here we are, and we're going to explain it to you
so
now
I say
so you don't have to come
it's
back and we have
it's
to re-explain it.
physics. It's physics. And then that's what I tell them, and then off they go.
Okay.
So
So how do we start? RF signal propagation.
okay, so you're already saying RF signal propagation. We're already like, what even is that? So I like to try to explain like an RF is really it's radio frequency. You can think of it just like the radio in your car. Same thing, right? So we're basically getting
Invisible waves going
yes,
through the air.
exactly. Propagating, traveling through the air, and it is part of the EM radiation,
Okay, electromagnetic spectrum.
Yes.
You have electric field and you have magnetic field. Alternating and propagating through space at the speed of light, for
And
example.
who found that out? James Clerk Maxwell.
Oh,
Oh,
and for
yes.
those who've forgotten already, Logan's last name is Maxwell.
That is true.
Oh, my son's middle name is Maxwell too.
There we go. There
So
we go. So we have them traveling through their EM radiation essentially, but think of it just like a radio in your car. You're dialing in at 91.5, right? And so that's going to be traveling through the air. As you can see, we have our air, we have our radio waves, right? They, depending on what they hit and what they're moving around, are going to either pass through something or reflect off of something. A lot of times, a combination of both, really.
right.
And so in our core markets, I feel like a lot of times it's manufacturing, it's industrial, it's heavy industry, and we're not in a lot of things that are just wood and glass, where everything just beautifully passes through everything and everything is hunky dory. A lot of times you're in metal walled with metal machines working on metal parts.
Or concrete and rebar.
Right. So, what that inherently means is lots of reflections of these radio waves as they move through space. Now, UWB is no different. We're just think about this.
Oh well, slow down.
It's just
Oh, UWB, you threw
is
in a new term there.
right. My mistake. So think about it, no matter what we're describing today, they're all moving through air. They're all going to either pass through or reflect. It's just part of it. That's
Right.
physics. That's how physics works. So we have different types of these waves, though, right? And just because they like to make physics hard, the narrow band is wide and the wide band is narrow.
I actually have an explanation for that.
Oh, please
So there's
do
time
tell.
domain and frequency domain. So
Mm,
the narrow band refers to the frequency domain of the magnetic spectrum. And so when you're in the time domain, the wave actually looks spread out, and vice versa for ultra wideband. Maybe that didn't make any sense at all whatsoever, but just trust us. The narrow band in the time domain is a large wave, and ultra wideband in the time
yeah,
domain is a spike, right?
yeah,
You say
yeah,
spike.
yeah, yeah, yeah. So the one person was just like, "Oh yeah, duh." Of all four people that end up watching this video, there'll be one.
They're like, oh yeah,
Yeah, yeah. There'll be one person be like, "Yeah, yeah, I get it, I get it." But suffice to say, what we're looking at here is you think of it same way. You're in a car, you're dialing the 91.5. That tower has generated a wave that is moving through to you through the air. Think of it like you're in a pool. Like this is a wave in a pool. Somebody did a cannonball. It's propagating out, right? And it looks like that as it's moving through. Okay.
a big old lumpy wave slowly propagating out from the center
Sure.
of the pool.
Exactly. And technologies that fall into this category on the left are
RFID.
almost all of them really mean
Uh,
Bluetooth.
Bluetooth,
Yeah.
Wi-Fi,
GPS.
GPS.
Yep. Yep. LoRa as well, I think. Right. Yeah, I mean, pretty much anything but ultra wideband is traditionally going to look more like what's on the left side of the screen right now, right? So, in a pool travels over you. Now, we'll get into why this is important in just a second, but really, why these are graphed over time is because we really need to know exactly when this wave hit us,
And this goes to, well, Logan, why is that the case?
right? So, in when we're calculating these things, we need to know exactly when the wave hit us and we need to know when it left. And that is a distance that it traveled because it's traveling at a constant speed.
RF, RF signals pretty much travel at the speed of light.
Yes.
And the reason for measuring those is get a distance. And if you get multiple distance, you know where something is. And so that's kind of the base of our solution in identifying where items are and facilities. Is that right?
Yes. So,
And that's not always the case for other locating solutions.
yeah, true. Yeah, you can do a signal strength, which has its own kind of difficulties. And then a lot of times there is just presence, an indication that something is there. Yeah, and a lot of traditional RFID is that way, and it works perfectly well for a lot of applications. But suffice to say, a lot of technologies, if they are traveling across, are going to hit you like this. And again, we're trying to measure a very specific time. We'll show that in a second.
Okay.
So, ultra wideband, on the other hand,
So move to the right side.
looks would look it would look very strange in a swimming pool, but essentially the wave as it's traveling is a spike.
Ooh.
Yes, so it's just one, but the benefit of that is that I would know exactly when that wave hit. There wouldn't be any sort. I wouldn't know. Hey, when did it exactly crest and hit me? This would say, nope. I know exactly the time that this wave
Gosh,
hit.
the spike, does it stab you?
If you are in a swimming pool and see a wave shaped like this, you should exit that swimming pool. Something is very wrong in the swimming pool. I don't think it will stab you, but you shouldn't stay to find out. You should leave the swimming pool.
But suffice it to say, with the stopwatch, you could definitely know time when it traveled from one point to another.
Yes, absolutely.
Much more so than the large, lumpy, narrowband wave.
Right. And so, again, getting back to time, right? Time is distance because RF travels at a fixed speed. So we know it's traveling roughly 1 foot per nanosecond.
Oh, nano. Okay.
Yeah.
Just to go back, 1 billion nanoseconds is 1 second. So 1 foot per nanosecond, if you can wrap your head around that. I am approximately 2 nanoseconds from Logan right now.
Yes. So are we time traveling? Okay. Anyways, so RF is traveling at a near constant rate of about 1 foot per nanosecond. So, billionth of a second, it's traveling 1 foot. So, we know it's traveling at that rate. So, how long it takes, AKA 2 nanoseconds from me to Seth, right? We can say, well, that's how much the distance is. If it was 2 nanoseconds, it's 2 feet, right? So, using now distance, right? Accurate time equals accurate distance. We have multiple distances. Now we can find something. Because we have multiple distances we can triangulate in and find where that thing is. So it's all about getting accurate time. If I can get accurate time, I can get accurate distance. If I can get accurate distance, I can get accurate location.
And just to compare it to other solutions, a lot of the Wi-Fi's and Bluetooth, the customers we talked to who've kind of downplayed this technology is because they've had previously bad experiences with other RF solutions. And to be clear, ultra wideband is a very different technology than Bluetooth and Wi-Fi tracking.
Right.
Oftentimes Bluetooth and Wi-Fi use proximity or they use signal strength, which is very different and not reliable in reflective environments.
Right. And here's why.
Oh my gosh. Now I am not in school anymore. What is this?
So this if we slow down and we calm ourselves, it's not too complicated, but essentially the waves we had before on the left side of the screen and the right side of the screen,
Right.
right? We now are showing them in a reflective environment.
Okay, so there was a wave and there was a barrier. So there's a non-reflective wave that also part of it hit a barrier, and now you have a reflective wave, and now they're combined. Is that right?
Yeah. So if you're in a pool and you have
So,
multiple people, or really truly just one person doing cannonball, and these waves are bouncing off the walls or other people, the waves that are coming back
uh-huh.
are combining with the waves going forward, right? And so they're going to sum naturally to each other. And so we're going to have a mix of those waves. So you can see we have a direct pulse that's in the blue. We have a reflected pulse that hit the wall of the pool and now is hitting us, right? And so what we perceive and what we measure ends up being the sum of
This
those.
green one. Is
Yes.
that right?
Yes.
And so just to be clear, this rectangle we're zooming into that rectangle of those blue and green lines, and that's what we're seeing on the right.
Yes. And it may be that each one of those tick marks is a nanosecond. Well, that's feet already that you're off, right? And it's
Right.
probably a lot more than that. So even just small reflections in these spaces can be the difference between 20 feet, 50 feet. And this is
Oh, easily more than
why when you're using these time domain technologies, you're not going to get accuracy, maybe to the room. And a lot of that is using signal strength and, proximity
so
detection.
what you really want to measure is this blue line intersection, but because of the reflections and the fact that this has such a low slope, I guess, or relative to any accuracy, is you're measuring something else, and it can be many feet off or hundreds of feet even.
Yes, very far off. And it depends. And this is always going to vary on your environment, but a lot of times you have a lot of reflection. It's going to be very difficult to get these sorts of technologies to work with accuracy. So you make up with that by dumping in 600, pings a minute, or, a whole bunch of readers every 10 feet.
And we've heard of that,
Yeah,
right?
yeah, yeah. I'm
There
not.
are facilities out there with
Yeah.
Bluetooth readers every 10 feet everywhere to get the level of accuracy they want.
Yes, yes, yeah. There's a
And
specific few sites that I'm thinking of, and yeah. Anyways, yeah, call us
okay.
eventually, please. So if you're looking at one side of the screen, that is reflections are much harder to measure. If you look at the wideband, aka the weird traveling water spike, when it reflects in its own pool, it is much easier to determine where that reflection is and sort it out from the true pulse, which is the true time.
Okay, so here the blue one is the true pulse, and
Yep.
the red one is the reflective pulse. And it would
Yes.
make sense the red one would come after the blue one because it has a longer distance to travel,
Yep.
and much more resolvable.
Yes. And so the sums, instead of it being this gummy sort of thing and construction, deconstruction, we can say that's a reflection. Get it out of here. It's not the true pulse, which means we have true down to the nanosecond, which means we can get you accuracy to the foot level.
Yeah, and ultra wideband actually allows picosecond resolution, so you can definitely get sub-foot level resolution as you need it.
Yes. And so even at a fundamental physics level, there's a separation in these technologies. Now, Wiser has done a lot more than just use ultra wideband. We've made it very cost effective and easy to set up. And that
Yes,
is
it's
very important to say.
oriented towards the highly metallic manufacturing environments for ease of use as well.
Yes, right. So it's already at a physical level, mathematically, it will be much more difficult to get these sorts of. So why we wanted to make this video is there's just fundamentally a split in the technology tree of what you're trying to use for these. Now, we've taken it even further, and we've done a lot of things to make it cost effective, easy to set up. But when you're trying to say, why will Wiser work and how does it work in these environments when we've tried all these other things? At a fundamental level, this is the beginning of that technology difference.
Absolutely. Very different technology and oftentimes very different implementations of different technologies. Is there any more slides? Or are we all done?
That I wanted to keep it brief. I'm sure we didn't.
So next time you're in a pool and you see a spike wave coming at you, what should you do?
You should exit the pool. So you could also reflect on your time with Wiser and think about ultra wideband technology, but you should really probably also get out of the pool. You should get out of the pool.
I can't imagine what reflecting spike waves look like in pools, but I guess that's for my own imagination.
That's for another video. That's for another video.
Have questions, want to reach out, how do you do it?
Contact us, email, contact us, forms. We also have phone, social media, really anything. Just let us know.
Yeah, Spike Wave Messenger service.
Yep.
Please do. Okay, I think we're good for time here. Thanks so much, you guys, and looking forward to the next time. Take care.
Bye.